All right, cool. So let's just go through the answers to the first quiz, which was on isomers. I'm not going to go through it in full detail with the Achieve Merit and Excellence. The main thing for me is to show you how to process the question, because you do have a link to the answers on the NCEA website. So this first question is pretty straightforward. It just asks you to draw the anatomers. The main thing that you need to do to start this question is to figure out which one's the chiral carbon. So with the chiral carbon, you're looking for a carbon that has 4 different things attached to it. So I can rule out very quickly that the ones with multiple hydrogens aren't the chiral carbon, because they obviously have the repeated of the hydrogen. This here is the chiral carbon then. And so when I'm thinking about the 4 different units, we have that ethyl group, we have a chlorine, we have a hydrogen, and we have a methyl as well. Doesn't matter which way you draw it. Personally, I like to keep it simple for me, and I put the long kind of chain at the top, and then I tend to do the short things on the side. Like that. The reason why is because then when I flip it, I can flip 2 small, easy things, and so the stuff that's kind of bigger stays in the same location. So I find that it's good for me to draw those out because people tend to struggle with that. Explaining, that's just your typical depolarized light. Also make sure that you mention about how they are similar as well. So if we're looking at the marking schedule for this question, you can see that both of them have been drawn. You don't need to draw it in the exact same way that they have drawn it. The main thing is that you've drawn it as optical isomers, and you correctly flip them around. So it doesn't matter that I have put my ethyl on the top and they've put their chlorine on the top. The main thing is I've done the drawings correctly. This is a really easy merit point because basically if you can draw both those structures, you're going to get the merit. And in this case, they wanted you to also do the justification as well. And that's a really easy justification, just talking about the rotation in plane polarized light. Make sure you are detailed with it, because the achieved is just identifying that they will rotate differently. A merit will understand that they rotate in opposite directions. I've also seen on marking schedules that part of the criteria for the answer is looking at how they are similar. So they have the same physical and chemical properties. The only thing that's different is that rotation in polarized light. Cool. All right, let's move on to the rest of the question. This one here is starting with that flow chart. And my main kind of suggestion here when you're going through it is annotate it before you start filling it in. And also don't worry about not answering it in order. If you need to work backwards to figure it out, work backwards. This also kind of highlights that importance of knowing major and minor, Zetas rule, Markovnikov rule, because obviously we need those products to be able to keep going forward. But even if you aren't sure which one's major, which one's minor, like I said, you can use the hints from earlier to kind of work yourself backwards. So KOH and alcohol, that one is going to be elimination reaction. And this is why you should start memorizing those reactions early. In this case, I would then expect an alkene here. Then I see that there's a minor product and I see HCl. So that hints to me that we have an addition reaction. And from that addition reaction, we're making a haloalkane. So like I said, use the hints that are there to kind of help you figure out what's going on. I know this can't be a substitution reaction, because if it was a substitution reaction, I would only have one product, and that would be this chlorine swapping in for an alcohol. So there's things in the question that logically you can use to help you kind of figure it out. Cool. This one to this one, we haven't done amines yet, but that is an amine. And I can see that it's on carbon number 1. And so that one's a primary one. So what that tells me then going backwards is that my haloalkane must also be a primary. So like I said, if you aren't sure what you are dealing with, use the rest of the question to help you out. And with this here telling me it's a primary haloalkane, that can actually give me a hint that I've done the CH. I have that because the only way I can get this is from a primary halo alkane. So that's what I'm saying. Use the hints that are there. Even if I wasn't sure what major or minor was, I could still figure it out going backwards. Alkenes are really important as an intermediate step because what these alkenes can do is it can shift functional groups down. So that's basically why we've made an alkene, so that way we can shift the halo alkane down. I'll fill that in real quick so you can see what I'm talking about. And that is my minor product, because when I look over here, that has 3 and that has 2. So my major will have the double bond between carbon 2 and 3, whereas my minor would be 1 and 2. So that all ties into what we've been doing previously and verifies each other. I can see in this case that I have KOH aqueous, so keep in mind those little symbols. That is a substitution reaction. I can verify that's a substitution reaction because when I look over here, I have a carboxylic acid. And the only way I get a carboxylic acid is by oxidizing an alcohol. So we can see how we can use that information to help. And so what I should have here is an alcohol. And this is something that you guys have covered last year, but we will have some more lessons on this oxidation process. And then again, it's just about memorizing your reagents for those last two. If we look at the answer schedule, reagent 1 was the ammonia. That's alcoholic and it is also concentrated, or you can remember it needs to be an alcohol for that ammonia, because if that ammonia is in water, it's going to react with the water and you're going to get the ammonium ion, which won't work. And in this case here, we can use any oxidant. Oh, you can't see my screen, that's why. Sorry, ammonia here. And this, I can use any oxidant, and we'll have that in later lessons. Cool, so you can actually do most of the flow chart. I've actually cut off the last part which has D and reagent 3 because we haven't covered that material yet. Cool. All right, question C, I've only given you a very small portion of it, which is number 4. So do keep that in mind when you're looking at the answer schedule, that there's lots of various answers in there. But it starts getting you looking at these molecular formulas and using the molecular formula to figure out isomers. So in this case, we have carbon, hydrogen, and oxygen. So the first thing I do when I'm looking at these questions is I try to check my carbon to hydrogen ratio, and I see that it's ×2. So what that tells me there when I see it's only ×2 and not ×2 plus 2 is that there must be a double bond. So do kind of keep that in mind as various hints, because if you saw the full question, basically I think it's like 1 through 3, and then there's 4 and 5, are all just giving various descriptions of the organic compound, and you're using those hints with that formula to figure out what the molecule is. I've only given you number 4 because we haven't learned the molecules for the other, or we haven't learned the function groups for the other molecules. So I can still figure out this one because it gives me some information. It's a straight chain, so what that tells me is there's no branches, and that it decolorizes with bromine water. So when I see that there must be an alkene, there must be a double bond, because that's the only one that decolorizes with the bromine water. And it can exist as cis-trans geometric isomers and also anatomers. So it helps me kind of know where to place the double bond, and this tells me that I must have a chiral carbon. So all that information helps me figure out what I'm dealing with and ruling out various isomers. So if I have 1, 2, 3, 4, 5, I need to think about where the double bond goes, and I also need to think about where the, in this case, the alcohol has to go. The way I know it's an alcohol is because I have a double bond. That tells me the double bond is in the currents of an alkene. I see that my formula also has oxygen in there, and so in this case, the only function group that I know of so far, and that works with this example, is that I have to have an alcohol to provide that oxygen. We will learn about other functional groups that also have alcohol, or that also have the oxygen in it, but in this case, it's just alcohol. So I know it's not going to go between, or sorry, let me backtrack. I know the double bond won't go between carbon 1 and 2, because if it went between carbon 1 and 2, I won't be able to have geometric isomers. So that's how all these hints need to play together. For me to have geometric isomers, it needs to go between carbon 2 and 3. If it goes between 3 and 4, it's then still between carbon 2 and 3. So I've already figured out where the double bond's being placed, and now what I need to figure out is where does the alcohol go. I need to place it somewhere so that way there's an optical isomer. So I can't place it on carbon number 1, because if I place it on carbon number 1, all my other carbons will have hydrogens, and that means that all the other carbons there won't have optical isomers. So let me just draw you an example. So if I had this, there's no optical isomers in that example. It does meet that cis-trans geometric isomer requirement because of these two carbons here. But when I go through each one of those carbons, they don't have 4 different things attached to it. So no optical isomers in that example. So that's how I ruled out that one. So let's draw that initial structure before. The alcohol cannot be on carbon 2 or 3. Same issue, I won't have any optical isomers. The carbons with the double bonds obviously can't be a chiral carbon because of the double bond being present, because we need 4 things attached to it, and the double bond prevents 4 different things being attached. So I can rule out these 2. I've already ruled out N carbons for the same reason, so I know it must be on that carbon there. And when I go to fill it in, I can see that this carbon here has a methyl attached to it, an alcohol attached to it, this long chain with a double bond, and then a hydrogen. So that's 1, 2, 3, 4. And that's how I figure out it's that structural formula. So yeah, if we see that's the answer for number 4. Obviously 1, 2, and 3 we'll talk about later, because I need to teach you what those functional groups are. This is what I like. This is a good example of what organic chemistry is like. There's not a lot of writing with organic chemistry. You look here at this question number 2, and there's barely any writing. The points come from your processing and your ability to kind of integrate information together. And that C question 4 is a really good example of can you integrate information together. And that C question does go up to the excellence level, and it's just a matter of can you figure out all 4 structures? And then the other points are based off of do you get 1, do you get 3 of them? So it's a good example, like I said, of the difference between organic and thermochemistry, because thermochemistry has a lot more writing. Whereas this, it's all can you process. Cool. All right. I hope that makes sense. And I'll keep recording some more stuff for you.